So last time we started into chapter 9 and we talked about a few different things. First off, we talked about really the different types of forces that hold together really one molecule with another molecule. And those are basically what are referred to as intermolecular forces. So we talked about different types of intermolecular forces. And again, that's pretty much the thing that holds together, like I mentioned, two different molecules. The basic sort of attraction, as we talked about with our sort of intermolecular forces, is the basic attraction between something that's really positively charged or the positively charged of one side of a molecule and like the negative charge of another side. So sort of that electrostatic attraction. um, and there's really sort of three main types of intermolecular forces that we oftentimes come across. And those three different types, as we talked about, are uh, hydrogen bonding, dipole dipole interaction, and dispersion forces. And each of these really have sort of as we talked about, a class of molecules that basically sort of is what they use as a way that, again, one sort of molecule interacts with another molecule and sort of holds them together. Starting with, say, dispersion forces, this is really the main attraction that we see in anything that is sort of a nonpolar molecule hanging out with another nonpolar molecule. That is kind of the main force that we see when these nonpolar molecules get together. In reality, though, everybody could use some type of dispersion forces, but this is really the main sort of force that happens there. These are these weak temporary forces. So there's a couple different ways this could sort of occur, but one main way that it occurs is through what is sometimes referred to as an instantaneous dipole. And that's when something that is normally has no charge, electrons decide to kind of go one side of the molecule versus the other, and it gives it a temporary sort of separation of charge within that molecule. And that affects another nonpolar molecule that may be near it, giving it also a temporary sort of distribution of charge within the molecule. And now they have a way to interact with each other. These are weak, these are temporary as the electrons could shift back. Obviously, these interactions would break, new interactions would be made. And again, it's sort of a weak sort of interaction because of that. Another way is we talked about that you could actually induce this sort of dipole to happen by adding something like that has a charge, like an ion, some polar molecule. And that's what we talked about, that, when you do mix something that's, say, polar with something that's non-polar, there is a moment there where it has an ability to sort of hang out with each other and sort of mix a little bit. But for the most part, it will sort of separate out because it doesn't have a long range way of maintaining those interactions, as these are dependent on really kind of developing these charges and then they kind of go away. So it's sort of a temporary sort of situation. Dipole dipole is really what we use with polar molecules and polar molecules. And these are guys that do not have the ability to hydrogen bond. So when we do have a polar molecule, as we talked about with bonding, or when we're talking about bonding, that means it basically has a fixed sort of dipole moment, right? So it has a dipole moment, which means no matter what the situation is, it's always going to have this sort of charge. And another polar molecule will also carry a similar set of charge. And again, that's where they get that interaction between them. Hydrogen bonding really is a form of dipole-dipole interaction, also is between polar molecules and polar molecules, but these are guys that obviously have the ability to hydrogen bond. In order to hydrogen bond, you need a bond between hydrogen and nitrogen, oxygen, or fluorine. And if you do have that, it has the ability to hydrogen bond. The reason you will get this hydrogen bonding occurring is, again, nitrogen, oxygen, fluorine are the three most sort of electronegative guys there on the periodic table, upper right of the corner, going to create a really polar bond between hydrogen and either nitrogen, oxygen, or fluorine. That's going to allow a big separation of charge between the hydrogen and the nitrogen, oxygen, or fluorine, and going to allow that positive negative attraction to occur. And again, that is sort of what we see here when we look at something like water here, hydrogen and oxygen together, give that big separation of charge, making this side more positive, side more negative, and again, going to allow it to interact with another water via that hydrogen bonding. In terms of relative strength, as we talked about, this is sort of the strongest of them all. That is the weakest of them all. Now, we also then talked about sort of different phases, and we talked about obviously going from, say, solid to liquid to gas and backwards, basically, and our different sort of transitions, obviously melting. We have evaporation, condensation. We're freezing if we're going this way. And this is obviously sublimation. And that is deposition coming this way. And we talked about sort of the energy required in all these sort of processes. Remember, as we go from solid to liquid to gas, that is all endothermic processes where heat and energy is put in. And as we go the opposite way, gas to liquid to solid, that is sort of an exothermic type process. Again, heat and energy needs to be released in these processes to do that. We also talked about the idea that, you know, there's a certain amount of heat and energy required basically to do this transition, and that's the heat of fusion. There's a certain amount of heat and energy required to do this transition, which is basically the heat of vaporization. And as we talked about, that's the energy required to do nothing more than actually just change the phase from, say, solid to liquid, or if you're going from liquid to gas. Remember that those phase changes do occur at the same temperature. And when you are at that temperature, which is either the melting point or boiling point, you basically have both phases in equilibrium with each other. So for example, for water, as we talked about at 0 degrees Celsius, you are looking at both solid ice and liquid water basically happening at the same time. Not until you get above 0 degrees, you got liquid water. Below 0 degrees, that you have ice. But right on zero, you basically have a combination of both of those sort of phases together. Any questions on that so far? Okay. We also sort of finished talking about sort of phase diagrams, and phase diagrams we can use to help us understand what phases something would be in a combination of, say, pressure and temperature. Pressure and temperature has a relationship, obviously, as to, you know, what state something would be in, what normal sort of diagram something would be in. So we talk about phase diagrams, and remember, we can use those to determine, again, sort of pressure temperature relationships, where we expect to find something to be in solid, liquid, or gas. Phase diagrams show the three different phases. They do show the kind of transitions where you go from solid to liquid to gas. And obviously, we see some other things that we talked about that were important in there. There's the triple point on that diagram. That is the point where you have all three phases in equilibrium with each other. There's also the kind of critical point, which is where you find your critical temperature and critical pressure. And again, in sort of that phase diagram at that point, if we kind of follow it along here, This was liquid, this was gas. That's that point right about there where, again, the liquid phase sort of flows into the gas phase, and we get what is sometimes referred to as a supercritical fluid sort of in this area of that curve. Again, solid kind of being over here, triple point coming here, extra line there. But that triple point right there, again, where all three phases come into contact. So as we talked about, you do need to know sort of what a phase diagram looks like, where all those things are found, and obviously be able to use that to answer questions about, like, you know, what phase you would expect something to be in. Remember that about 1 atmosphere is considered standard pressure. So when you're looking for like the normal boiling point or melting point on, say, a phase diagram or something like that, you know, kind of 1 atmosphere is, you know, usually where you want to go across, and really those lines and those pressures, temperatures at that point would be where you would find those normal melting and sort of boiling points. Any questions on anything we talked about last time there? Okay, then let's pick up and kind of finish up here. We're going to kind of talk a little bit more about water, a little bit specifically here. I'll spit that out, I think. And then we'll get into a little bit of solid and kind of be done, I think, with chapter 9. So water obviously covers a lot of the world in our ocean here. It has the largest thermal conductivity, has a lot of surface tension, as we talked about last time. Again, due to the very strong intermolecular forces of hydrogen bonding that it uses. Most of the properties that it consists of are because of hydrogen bonding. One interesting sort of property of liquid water, or water in general, is something that's different than a lot of other substances. Remember that a lot of other substances, when we get to the solid phase of it, is much more dense than, say, the liquid phase. And that is sort of opposite here in water. And it's due to that hydrogen bonding, as we talked about. We'll see a picture of in just a second. But because of the way it comes together, water in the solid phase to form ice, it actually ends up being less dense than liquid water. And again, that's why our ice cubes and our drinks and stuff will float rather than obviously sink when we put them into our cups. And again, that's a very unusual sort of property of a substance. When we do get it, again, remember, as we talked about, it is hydrogen bonding happening there with our water. And again, water having that dipole moment, which is a fixed dipole moment, making this side more negative, this side more positive. So again, when we do get those waters together, this side being more negative, this side being more positive, the hydrogen from one, again, bonding to the oxygen of another, as that is more negative here. And we're able to do that hydrogen bonding because of the oxygen attached to the hydrogen here, making this bond a really polar bond, right, based on electronegativity difference. Also, a good reminder, as we talked about last time, that, you know, just because something does have hydrogens in it, as we saw, for example, with CH4, it does not mean it has the ability to hydrogen bond. It does need to have, again, that oxygen, nitrogen, or fluorine sort of involved. And that's, again, what we see here, our intermolecular forces. And again, also a reminder, something we talked about last time, these intermolecular forces that we're talking about are always much weaker than these sort of bonds, which are intramolecular forces. So intramolecular forces are the forces within a molecule, like the oxygen-hydrogen bond here. And those are always stronger than a intermolecular force. And as we talked about last time, again, from this picture, the reason we know that's true is, again, when we heat up something like water, the first bond that breaks is actually the bond between the separate water molecules, which allows these water molecules basically to come off as whole molecules. Again, if it was opposite of that, what you would see is these bonds here between the hydrogen and oxygens within the molecules would start to break down, and you wouldn't get water molecules or steam that would come out when you start to boil water. You would get hydrogen gas and oxygen gas, which again, you don't get Otherwise, that would probably not be, again, a very good thing to occur. Now, when we talk about water, again, some of that unusual properties that we do see with water, water, it really does expand when it freezes. So example, we've all probably done this perhaps at some point, put liquid water in a glass jar into a freezer, or probably in a lot of people's cases, threw like a can of soda or something like that into the freezer to cool it down, forgot about it. And then when you come back and you go grab your can out of the freezer, the bottom is no longer square. It's now like bulging out the bottom, right? And that's because, again, as it's in there, those water molecules are freezing. That can's under pressure. It's got really nowhere to go but to force more pressure onto the can itself, and it starts to kind of bulge out the bottom. Again, as we talked about, most molecules in their solid phase are more dense than in liquid phase. And again, that's a very difference that we see with water. And on the left is sort of liquid water, and liquid water, they're close to each other. They have a lot more room for movement. But as they continue to freeze, these molecules again start to arrange themselves in a way that's beneficial in terms of sort of the positive side of one molecule and the negative side of another. Remember that when things come together with these sort of intermolecular forces, what they really try to do is maximize the attractive forces and minimize the repulsive forces. So again, as they come at that solid, they have a lot less energy. They do try to kind of move themselves around and orient themselves around to maximize that attractive forces. The result of that in water and ice is it creates all this open space between the different water molecules, as you can kind of see here in this picture. Open space means overall this whole thing has a much larger volume. And again, as we talked about, when we think about density, which is mass divided by volume, by increasing the volume, the density will go down, right? Small number divided by a larger number gives us a smaller number for the density. So we see that sort of less dense ice development there, where it will really start to freeze. Any questions on that there? Now, another interesting thing when we do talk about water and ice and things freezing and density, for example, density, as a reminder, is affected by temperature. So as the temperature changes, so does the density of a substance. And when we talk about liquid water below 4 degrees is bloated with ice crystals. When it warms from about 0 degrees to 4 degrees, its volume decreases because ice crystals collapse, resulting in a greater density. And liquid water around 4 degrees Celsius has a density of 1 gram per milliliter. That typically is the density that we use for water. If you're ever asked, what is the density of water, 1 gram per mil is typically the one that you use. But you should be, again, cautious that, if this is a specific temperature you're dealing with, you may need to go to a table to find the density, because it, again, does change with temperature. But outside of more specific sort of question, if you just need the density of water, usually 1 gram per mil is good. But again, it really does change with temperature. So if it's some specific temperature you're looking at, sort of non-room temperature-ish, you should really take a look and sort of see what the density is at that point. So what does that mean? Well, it means that water freezes from the top down rather than from the bottom up, which is really good for, life that's swimming around in like lakes, oceans, and things like that. So for example, what ends up happening is we get that 4-degree warmer water, and that becomes more dense, so it floats to the bottom. We get the colder water that comes to the top, and eventually will start to freeze at the top of, say, the surface there, leaving the underneath water sort of insulated and still liquid water, which is good, which is why fish can still swim around in there and all that good stuff, even if the top is sort of frozen. The opposite would be true, obviously. If it froze from the bottom up, everything would be pretty much gone, right, in the waters there. if the water started to freeze from the bottom up, all the sea life and everything would be not so good. As we could kind of see here, um, we got this water here, and again, below 0 degrees, we got all the ice that's sort of happening up on the surface, insulating the bottom, the warmer water coming down here. Our fish here, even though he looks like he's in an ice cube, he's not in an ice cube. It's just bad clip art there. But our fish here, which we like to call Melvin, why not Melvin the fish there? He is swimming around and he's happy again because the warmer water is going down, colder water sort of going up and freezing. And again, allows obviously all the sort of sea life there to be in okay shape as this water is sort of freezing, which is why you could kind of go ice fishing, I suppose, and you still have water underneath there. Why, if you walk on a lake that's frozen or something like that, it's really not fully frozen. You fall in, it's still cold water underneath there. It's not solid ice all the way to the bottom or anything like that. Any questions on water there? All right. So now that we talked a little bit about sort of liquids and water and stuff like that, we're just going to talk briefly about some aspects of solids and sort of how solids come together and some different types of solids and some calculations that involve sort of different solids and how they sort of come together. So first off, now we're talking about really the solid state of matter. And in the solid state of matter, obviously everybody is packed in there really tight. There's really not a lot of room for movement. Things don't really have enough energy to kind of go past one another like they do in the liquid state. And obviously, as we've been talking about here, typically speaking, they are more dense sort of with each other in this state. They're typically rigid, which means obviously they're very hard to change the shape of it. Again, if you take like a countertop or something like that, that's a hard, solid surface there. You can't just take it and fold over the countertop into some different shapes or anything like that. It's very hard and hard to do that. As opposed to a liquid where you can take the liquid, pour it into some other container. It now has sort of a different shape of the container or whatever it may be. Now, there's two main types of solids: a crystalline solid, which is these very ordered arrangements of individual particles that's reflected in planar surfaces. And these basically are things like ionic compounds, like salts, that have very long range order. And what that means is when they come together in the solid state, they really do align themselves in a very, very organized and long range organization sort of pattern. And when we talk about something that's ionic, obviously they're going to arrange each other probably near with the cations and anions near each other as a positive negative guys, also trying to minimize that positives near positives and negatives near negatives. Now, another type of solid, which is a amorphous solid, really do not exhibit long range order, but they do have definite shapes and are hard. Things like glass and organic polymers or amorphous sort of solids, they really don't exhibit that long range order. And when we're talking about something like a crystalline solid where there is that long range order, there is, as we will talk about here in just a second, such a repeating pattern of this order that you literally can take as a small snippet of it, kind of a little small picture of it, and you can recreate kind of the entire structure just from the small little part of it, because there is such this repeatability of pattern that occurs as these solids basically come together. And that brings us to a crystal lattice. And a crystal lattice, when solids are allowed to cool slowly, and here we're going to be really talking about crystalline solids here, guys that really have a lot of order and stuff like that. When they're allowed to sort of cool slowly, the particles and liquids, again, as we talked about, will try to arrange to each other. There's a little bit of movement that occurs to maximize that attractive forces, obviously minimize that repulsive forces. The result of that is, like everything else sort of in chemistry, the goal here is sort of lower energy. So when we get everything sort of arranged and minimizing everything and moving things around to maximize those attractive forces, we're also allowing sort of an overall lowering of the energy of that sort of substance. And that's again usually a very more stable situation for something to be in, is that lower state of energy. The results are generally a crystalline solid. The arrangement of these particles are in what is sometimes referred to as a crystal lattice. The smallest unit that shows this repeatable pattern is what is called a unit cell. So a unit cell is what I was just mentioning sort of a second ago, is that part of the sort of structure that you could kind of like cut out that little part of the structure, take it out, and you just basically keep stacking that same little part of it. And you can sort of rebuild the entire sort of three-dimensional structure sort of from it. So let's talk a little bit about unit cells and sort of what should be sort of chosen as a unit cell and why we choose sort of certain things to look at as our unit cells, and other things would not be a great unit cell. So unit cells are these three-dimensional, usually containing 2 or 3 layers of particles. And again, unit cells repeated over and over will give the bigger crystal structure, again, sort of rebuilding the entire structure from this one little part of it. Starting anywhere within the crystal results in the same unit cell. Each particle in the unit cell is a lattice points. Lattice planes are the connections between these type of unit cells. So let's say we had a solid that sort of arranges themselves in a, like we have on the bottom there, sort of just, we call these circles here. These circles come together in this sort of solid form here. And they come together in their 3D sort of structure, right? Now you may be thinking, well, it would make sense that, hey, if I wanted my unit cell, I would grab, maybe something like this. Just grab this guy. And that guy does give a lot of information. If we chose that as our unit cell, we obviously would have a unit cell with basically a whole atom in there. And you may think that's probably a very good choice. And in this case, it's actually a bad choice. And it's a bad choice because although we do have plenty, 100% information about this individual atom or molecule that's here, we have really no information about where the next neighboring atom or molecule sort of is. Do we stack it right on top of each other? Do we stack it like off-centered or something like that? So although it may think wise to choose one that contains a whole entire molecule there, it's actually not a good choice in terms of a unit cell, in terms of picking something that helps you recreate the entire structure. From that sort of picking right there, we would not be able to understand the relationship between sort of each atom and its neighbor. Now, if we chose for our unit cells something like this, where we kind of take a little bit of that guy, a little bit of that guy, a little bit of that guy, and a little bit of that guy as our unit cell, we end up with a unit cell that looks something like this, where we got a piece of that guy's molecule, a piece of that guy's molecule, that guy's molecule, and that guy's. Now, this guy does give us a pretty good information because we now have some relationships between neighboring sort of atoms or molecules, which means when I kind of put another unit cell right on top, I know I got that going there, I got that going there, I got this guy going there. If I stack this guy over here, I got that, 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 and that. If I stack one down here, we have that, 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 and we keep going. We can now obviously rebuild this entire 3D structure because the unit cell contains information not just about one of the atoms or molecules present in this 3D structure, but it does contain information about its neighboring and how they sort of are arranged near each other. So it gives sort of location information within the three-dimensional structure. And again, you could continue to rebuild that. Obviously, it would have a guy down coming this way. And again, if we plop one there, we would continue to build out and so forth. And again, just by repeating the same pattern, you can see we're starting to rebuild that 3D structure. So that's why it's really important when we kind of choose a unit cell like we did here, for example, on the bottom there, they have information about these 4 sort of atoms and how they sit near each other. And in addition, you can see in this sort of relationship, there's actually a whole atom in the middle that's in relationship to these 4 other ones. So it gives you a lot of information, not just about one guy, but how they kind of sit next to each other. And you could kind of repeat those sort of patterns. So when we choose unit cells, that's sort of the goal there, is we want to make sure that we are, when we choose a unit cell, we pick one that, again, basically has that relationship where it's not just about one, but it's about how it sits next to all its neighbors. There's 7 different types of unit cells. There's cubic, tetragonal, monoclinic, all those kind of guys there that you see on the screen. We're just going to look at sort of simple examples of this. It can get very complicated, but we're just going to look at sort of simple cubic ones, where basically everybody's 90 degrees from each other, kind of like a square, if you will, a cube basically, and we've got these nice right angles and stuff like that. So when we focus in on those, it will allow us to do some calculations a little bit easier because of that. When we talk about unit cells, the number of particles that each particle is in sort of direct contact with is what is referred to as sort of the coordination number. For ions, it's the number of oppositely charged ions it's in contact with. When we get a higher coordination number, it means there's more interactions, therefore stronger attractive forces that are holding that crystal together. So again, as they come in contact with each other in this sort of 3-dimensional space, that's what's referred to as coordination number, how many guys are really directly in contact with each other. As I sort of alluded to before, and again, we won't go into great detail about packing efficiency, but the idea here is, again, when things sort of come into their solid state, they really do try to pack themselves in the most efficient manner that requires sort of the less amount of energy, which creates a more stable sort of situation. There's different sort of packing efficiencies and ways that things can pack. We're not going to get too into that in terms of how that goes. So let's talk a little bit about cubic unit cells, which are the ones we're going to really sort of focus in on and some of the important information there. First off, they're all 90 degrees between corners of the unit cells. The length of all of the edges are equal to each other. And the unit cell is made up of a couple different things. When we look at these unit cells, if we pull out a unit cell that's a cube, in each of the corners, you will have basically an eighth of an atom. So if you think about a cube 3-dimensional space, there's 8 corners, right? So 8 corners, each has an eighth of a cube. So that's like 1/8. That's one cube. That's one atom. Spit that out, right? That's one atom completely with an eighth of an atom in each of the corners. If you have something that's on the face, if you kind of take a cube out, it's going to split the atom right in half, and you would have a half of sort of atom on the face of it, and you'll have a fourth of an atom on the edge within each of the cubes. Now we're going to be talking about cubes here and really not spheres. So cubes is the volume of a cube is the length cubed. So if you think about like density, when we talk about centimeters cubed, right? That is a volume, right? So that is 3 length measurements multiplied together, centimeters times centimeters times centimeters, and that is a cubic volume. So let's talk about these 3 different types of sort of cubic cells. And again, they have some different names and some different amounts of atoms present, and how we calculate the length of each of the guys on the cells there. First off is simple cubic, which is sometimes abbreviated as SC for simple cubic. And important with simple cubic, and we're going to go through each of these individually here in just a second, but simple cubic has 1 atom present, and that 1 atom is from the corners. Basically, there's 8 corners. Each of them has an eighth of an atom there, which gives us our one total atom that's present within that unit cell. It has a coordination number of 6, as it's in contact in 6 different places. And the length of each guy is basically 2 times r. R is the radius. So that's a value that's typically given to you. It could pack 52%, which is not so important for us. Another one that we're going to come across is one that's considered what is known as body-centered cubic. BCC is sometimes abbreviated as. And again, that is basically 2 atoms present within that cell. Again, as we will see in a close-up in just a second here, an eighth of an atom in each corner for one whole atom, and stuck right there in the center, if you can kind of see it, is a whole atom. One whole atom complete there. The length will equal 4r divided by the square root of 3 is how we would calculate the length. It has a coordination number of 8 because it does have that central atom there. And again, that gives it a higher coordination number than here, which means it's able to sort of pack itself more efficiently. Because of that, a lot more things in contact with each other, going to bring everything in tighter to each other. Last type of sort of cubic cell we're talking about, our unit cell here, is a face-centered cubic cell. And face-centered cubic cell, as we will see, basically has an atom in each corner. Then we have a half atom on each of the faces, giving us a coordination number of 12. And again, the length here is actually, it's kind of hard to see here, but it's actually 2 times the square root of 2, and it's times r. R is not underneath the square root, even though it kind of looks like it is. R, sometimes people go 2r square root of 2. So the r is actually not part of the square root there for the length, and we'll see a better shot of it there. But it does have 4 atoms involved here on face-centered. So really important for calculations are these 3 things. Obviously the name, the number of atoms that are present, and how to calculate the length. And those are really 3 things that you do need to know in order to sort of do these calculations. So let's take a little closer look at each of these here and sort of see where we're talking about these atoms sort of come from. Let's start with simple cubic. So simple cubic here, again, does have an eighth of an atom on each of the corners. So basically 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8. 8/8 of an atom is equal to 1 whole atom that is present here in the corner. Again, as it gets sliced and you kind of pull out all the unit cells that's above it, to the side of it, behind it, and all that kind of stuff, you're left with only 1/8 of an atom there. The length there of each one is 2 times the radius, which is really important. So simple cubic, 1 atom, length is 2r. Really important for doing that. And again, here you can kind of see the wedge here of 1/8 of an atom that occurs here on each of the corners, and our coordination number here of 6, basically 1, 2, 3, 4, 5, and 6 sort of interactions with this guy here. So 1, 2, 3, 4, 5, 6 in terms of the coordination number. Here's a closer look at it. Again, the length being 2 times r, and again, eighth of an atom coming out in each of those corners. The next one is a body-centered cubic cell. And again, a body center is a little bit different than the simple cubic in terms of what's happening here. So when we pull out that as our unit cell, we do get a couple of different things. First off, we get the eighth of an atom in each corner. So 1, 2, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8 for a grand total of 1 atom from there. And dead center, hence why it's called body centered, because in the body and the center of this unit cell is 1 whole atom itself. And that gives us a grand total of 2 atoms that are present here in this type of unit cell. The length of it is 4 times the radius divided by the square root of 3. The rest of the square root got disappeared there. And the r got disappeared, looks like it. So that's 4 times r divided by the square root of 3. Again, coordination number here is going to be 8. So let me rewrite that there, 4r square root of 3. And again, as a larger coordination number, able to sort of pack in, we get some interaction with the guy in the center as well, which allows everybody to sort of come together. So again, here we see our 8th sort of wedge in each of the corners, and we see sitting kind of dead in the center of all those is a whole atom that's right there in the middle of the body, basically, of it. And again, these are coordination numbers of how they sort of come together: 1, 2, 3, 4, 5, 6, 7, and 8. Between, say, the purple and its oppositely charged sort of guy that's in the 3 dimensions. And it gives that much interaction, bringing all those negatively charged to these positively charged guys in, and bringing it packing in very more tightly than we see before in the simple cubic. And again, here is the length of a cell there. The last one is, again, the face-centered, as we talked about. Oops, come here. And our face-centered is a little bit similar here. We end up with our square root just jumped way too low there. Let's go square root of 2 over there. All right, so again, we have our 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8, giving us 1 atom present. Each of these sort of pink guys are actually on the face of a cube, and there are 6 different faces to a cube, right? So if you go top, bottom, sides, back, all that kind of stuff, these guys are basically going to get sliced right in half, each of these guys there, as it gets pulled out. And 6 times a half is 3 atoms. And this guy has a total of basically 4 atoms present within this cubic cell, with a length of, as I said before, 2 times r square root of 2. And again, obviously a lot more interaction happening here because we have all the half of atoms sort of on the faces. We get a lot more of those coordination number 12 sort of occurring. And you can see here we have our 1/8 of an atom in the corner and a half a slice of an atom, if you will, on each of the faces of this guy. Obviously, when we put it back together, we get an 1/8 on each of the corners and the other half, and we have our atoms sort of back together in this particular case. And we do have our 12 arrangements here with all the different colors sort of atoms that are present there. Again, a closer look at that sort of slice that's happening here. Again, a half atom on each of the faces, and there's 6 faces on the other side and on that side there. So again, really important on these is understanding the names and the type of number of atoms that are present and stuff like that. What are we oftentimes sort of asked in a situation like this? Well, a very common thing that we're asked is to calculate the density, which is mass over volume, of a sort of cubic cell. So they will give you some information about what type of cubic cell it is, and using how many atoms are present, the length of the radius that they typically will give you, you can actually calculate the density of these things. So let's go through a calculation here together to see how it works. First off, let's take a look at the next example, which should be an example of this. There we go. So here we're looking to calculate the density of aluminum as it crystallizes in an FCC and has a radius of 143 picometers. So first off, density here is mass over volume. So that's ultimately what we're looking for. And we're actually looking for it in a kind of our normal units of solids, which is grams per cubic centimeter. So you can think of these problems as really 2 types of conversions. One gets us to the grams part, and one gets us to the cubic centimeters part, which is the volume. So a couple of pieces of information that's really sort of important to us is, first off, this piece of information here. It is a face-centered. And what does that mean? Well, it means what we were just talking about in the previous slides. If we go back, our face-centered has 4 atoms, and it has a length of 2 times r square root of 2. So that's 2 really big pieces of information that you could get from it saying that is face-centered. So again, face-centered means 4 atoms. And we know the length is 2r square root of 2. All right, so how does this get us to each of these things that we need to sort of tackle? Well, the number of atoms can be very helpful if we just think about like a conversion, right? If I know the atoms and I need to get to grams, right? You know, how can I do that based on sort of calculations that we've done previously? Well, hopefully you remember when you see the word atoms, that should make you think about our good friend Avogadro and his number, the 6.022 times 10 to the 23 atoms per mole. So I could use Avogadro's number to go from atoms to moles, and then I could go from moles to grams because we know how to do that conversion. Going from moles to grams is the molar mass, right? So we could use some calculations that we've done before to help us get the top part, which is grams, and that's what we're going to focus in on at this point. So we'll do that. So let us go with 4 atoms of aluminum. Again, using Avogadro's number. And we would put it on the bottom here. I've now gone from atoms to moles. And again, I can use the molar mass to go from moles to grams. And it is 2698. And if I do all that calculation there, we will end up with 4 times 2698 divided by 6.022 to the 23. That's going to give us 1.79 times 10 to the minus 22, and these would be grams. So I've now, based on it being face-centered, have figured out the grams part. Any questions on that part of the calculation? Now what's left to figure out is actually the volume part of it. And the volume part can be figured out from also the face-centered and the fact that that is 2 times r times the square root of 2. And also the radius that was given to us. So the radius that was given to us in this particular case is that the radius of this unit cell here is 143 picometers, right? Now, let's talk about units here and ultimately where we want to kind of go to. We want to end up in a volume that's in basically centimeters, and this is in picometers, which means at some point along the way, you got to do a conversion between picometers and centimeters in order to get it into the right units. So another important relationship is obviously there is a 100 centimeters in a meter. And pico is 10 to the minus 12, which means in 1 picometer, there is 10 to the minus 12 meters. So at some point, you need to do that conversion. You could either do it up front, you could do it in the middle, but somewhere along the way there, you need to do that conversion. So we're going to calculate the length here. And I'll leave it in picometers here first to do it. So 2 times our 143 picometers times also the square root of 2. And if I do that, I get Looks like I get something like 404.47, we'll call it, or something like that. 404. Sure, I typed it in right here real quick. So we get 404.67, 404.47. I keep putting the 6 there, extra 6. Try that again. Try that again here. One more time here with feeling. 404.47. There we go. These units again are picometers. At this point, and again, you could have done it probably before as well. I'm going to do some conversions between picometers and centimeters because ultimately the goal I want is centimeters cubed. So again, remember that when we do this conversion, oftentimes messed up by people, 1 picometer goes on the bottom, 10 to the minus 12 meters go up on top. And then our 1 meter is 100 centimeters there up on top. And we end up with something with a lot of zeros. So we end up with 4.04 times 10 to the minus 8 centimeters. Any questions on that? So I basically put the radius into the formula. I did a conversion of units, so I don't forget to do it, and I end up with the right units. Any questions on that so far? Now, also a very common mistake and something you should keep in mind of is at this point we are in centimeters, which is not a volume. Remember that a volume is cubic centimeters. So here we're still in the length, really, right? Which is what the L stands for. So this is where the other thing that we talked about just a second ago that's important, which is the volume of a cube is equal to length cubed. So the volume is equal to length cubed, and that equals 4.04 times 10 to the minus 8 centimeters, and we're going to cube it here. So at that point, that gives us, we got that, and it's cubed. Looks like 6.62, we'll call it, times 10 to the minus 23. Again, when we cube the volume here, I'm sorry, the length here, we end up now with cubic centimeters, which is now a volume. And now what we're looking for in terms of our bottom guy, we are now good to go here. So we now have the volume. We calculated the mass. What's left is to actually put it into the density equation, which is our mass divided by volume. Our mass being 1.79 times 10 to the minus 22 grams, I believe, divided by 6.62 times 10 to the minus 23 cubic centimeters. Dividing those guys out gets us 2.71. Again, the units here are grams per cubic centimeter because they do not cancel, and that is the units of density. That is a long way to go to get to our density, but that is the density there of aluminum, and it actually is pretty close to the density of aluminum. Any questions on that calculation? So you can kind of think of it really as sort of two conversions. You just got to make sure that you're obviously using the correct length measurement, which is a common sort of error. Second error is not getting yourself into centimeters at some point. So again, that's a very common error. Third common error is not knowing how many atoms there are in a particular unit cell. And that obviously will affect your grams calculation. Any questions on any part of that calculation there? Okay, so why don't you try one here? This is the aluminum, right? That's the one we just did. don't you try this one here? Estimate the density. We'll do it in, go here, there. Estimate density of RB. It crystallizes in body centered. Has a radius of 247.5 picometers. We're looking for the density in grams per cubic centimeter. And I'll give you the molar mass of it. Of RB is something like 8547. All right, take a few minutes, see what you come up with. So you can just keep scribbling on the page here. Okay, let's take a look here and see how we're doing. So kind of want to approach the same way, kind of see what information we could get from this and what important information we get from the actual question. So first off, the first thing we'd obviously want to focus in on is that it is body-centered here. So body-centered, again, is basically our guy that has our eighth of an atom in each of the corners. And body-centered means we got one full atom sitting there in the center. So because of all those corners and the center guy, that means that we do have two total atoms here because it's body-centered. It also means that it has a specific length measurement or length sort of calculation, and that is that the length in this case would be the 4 times the radius divided by the square root of 3. So again, that's two really important pieces of information that we could get from the type of unit cell that we got going on here. We also do, which is very common in terms of radiuses given to you in our picometers. Again, we'll need our kind of conversion we just saw there, that 1 picometer, 10 to the minus 12 meters, and probably our 100 centimeters and a meter conversion. Again, here we're looking for density in grams per cubic centimeters. We could attack this the same way, starting with the grams part here because we do know atoms. So we'll do our Avogadro's number version here. So here we would be starting with 2 atoms in this case. Again, we use Avogadro's number on the bottom to get rid of the atoms per mole. And obviously we would want to use the molar mass from the periodic table for rubidium there, which was 8547. And if we do that there, that is 2 times 85, whoops, 2 times 85.47 divided by 6.022 to the 23, looking like 2.84 times 10 to the minus 22 grams. So again, that gives us our top part there. Any questions on that calculation there? So just to show you, last time I went into the length measurement with it in picometers. If you wanted to, you could convert the picometers up front to centimeters and then go into it. So we'll do it that way here just to show you it should come out the same. So if I took my 247.5 picometers, again, 1 picometer, 10 to the minus 12 meters, and 100 centimeters in a meter, that will give me 247.5 times 10 to the minus 12 times 100, 2.48 times 10 to the minus 8 centimeters. So again, you could do the centimeter conversion right up front and now put it into here. And if we do that, the length would equal 4 times our 2.48 times 10 to the minus 8 centimeters divided by the square root of 3. That will then get us times it by 4 divided by the square root of 3. Blah, blah, blah. 5.7 something there. 5.72 looks like. And again, as we mentioned just a second ago, we want to remember that this is not a volume at this point, as it's just centimeters. So again, it is still a length. So at this point, because all these are going to be cubic that we talked about, the volume will be the length cubed. And that would then mean we just need to cube that number there. And if we cube it, 1.87 times 10 to the minus 22. And that is how we then turn it into cubic centimeters and a volume, and really the bottom part of what we need. Last part is really just plug it into there. So in this case, our density will equal our mass, which was 2.84 times 10 to the minus 22 grams, divided by our volume, 1.87 times 10 to the minus 22 cubic centimeters. 2.84 ends up giving us a density of 1.52 grams per cubic centimeter there. Any question on that calculation there? So this is a common sort of unit cell type problem. Another common sort of problem would be kind of working it backwards, where you know, maybe you're given the density, you need to figure out the radius or something like that, or how many atoms or something of that nature. So kind of working it backwards from the density. Those are some common sort of questions. Any questions on how to calculate these sort of problems here? So again, the really important piece of information, as you can see from these examples, knowing obviously the three names, how many atoms go with those names, and obviously the calculation of the length, and making sure you get everybody into really the right units is sort of critical. All right. Hopefully they agree with us. Looks like they do, so that's good. All right. So we're not going to really talk too much about closest packing, but it's just to touch upon it. It's, again, as I was mentioning earlier, when we have these different sort of guys coming together in solids, they really do kind of try to come together in these layers and how they kind of pack themselves in there. And again, they want to be able to pack themselves in such an efficient way that it really does minimize energy. Again, a very common crystalline type structure is from an ionic compound, and ionic compounds basically arrange themselves together in this really repeatable sort of pattern, as you can kind of see here. And again, obviously, we have our negative guys or positive guys, negative guys, positive guys, negative guys. Again, they try to arrange themselves where they sort of maximize their attractive sort of forces and sort of minimize these repulsive forces that occur in these sort of patterns. And again, you can see if you kind of pull off that, you really will get a sort of repeatable pattern, as we've been talking about in terms of those unit cells. Any questions on any of that there? That should wrap up chapter 9 here. So we're off to chapter 10 here, and second to last chapter here we're going to talk about. So we're in the back 9 here, definitely. So we're obviously going to talk about solutions. So in this chapter, we're going to talk about solutions, how they interact, why certain things are soluble and insoluble in each other. We'll also talk a little bit about a little review of some concentration units that we've seen before in terms of solutions, like percent mass, molarity, some of those things. And then we're going to get into really the sort of heart of this chapter, which is sort of colligative properties and some calculations involving solutions, things about freezing points and boiling points and those type of things. So let us get into it here. So when we talk about liquids, when we talk about them being sort of soluble in each other, which basically means that they mix really well. Sometimes we talk about liquids and liquids mixing as being miscible in each other. So if somebody says that these two liquids are miscible in each other, what that essentially means is they will basically look like one sort of solution. It will all dissolve in each other, will really mix in each other. So if you take a solution that is really miscible in each other and you put it in with another liquid, it basically will just look the same throughout. So you really won't see any distinction between the different liquids. It'll just look like kind of like there's one liquid in there. An example of that is something like ethanol and water. So why would ethanol and water sort of mix? So if we look at sort of the structures there of ethanol and water is H2O, looks something like this. It is polar, which means, again, this side more negative, one towards the oxygen side, hydrogen side more positive. And ethanol is a guy that looks something like this. And ethanol is sort of an organic guy, and it's got kind of two parts to it. It's got this part here, which is pretty much all carbons and hydrogens and pretty much nonpolar. But it contains that OH bond there at the end. And that OH bond is really important for its functioning. This OH bond is pretty much the same OH bond as this guy, or even this guy here. Really, it's the same OH bond that we see in water. So although a lot of methanol there is nonpolar, it does contain this polar bond, which is partially positive here and partially negative here. That is not just a polar bond, but that's a bond with hydrogen. Not just a bond with hydrogen, but that's a bond with hydrogen and oxygen, which means that ethanol has the ability to hydrogen bond with something like water. And that's exactly what happens. So the hydrogen bonding here occurs, which, as we just talked about in the previous chapter, is an intermolecular force. And because they basically have the same type of interactions that occurs, they're able to mix really well. Ethanol is not a very big molecule, so it's able to mix and be okay. So because they do share those same intermolecular forces, it very much helps out in the solubility department and allows them to interact really well. Now, when we get two liquids that really do not mix with one another, those are what are referred to as being immiscible with each other. And when you do that, typically what you see is, some layering happening, like different liquids. And you see distinct sort of layering happening because they really don't mix together, and they're called being immiscible with there. So we take something like carbon tetrachloride with water and put them together. They really don't mix. So why is that? So if we look at the structure here, carbon tetrachloride looks something like this. I won't draw all the non-bonding electrons on the chlorines, but there are. But this is basically no dots on the central atom. We have everybody outside the same, and it's a symmetrical geometry. This is a nonpolar molecule, which obviously the water, which we talked about previously and many times, is a polar molecule. So really, the big reason why things sort of mix and why things don't mix, the big reason for that is the intermolecular forces. So when we take something like carbon tetrachloride, it's nonpolar, which means it's going to try to use dispersion forces as really its only way of interacting, which are those really kind of temporary sort of forces. Water is definitely going to use hydrogen bonding as its force. These are two different forces. These are things that over the long period of time cannot maintain interaction with each other. This guy temporarily could produce a positive negative, but again, will eventually kind of break back apart into a neutral sort of guy. Hydrogen bonding, this guy's polar, which means he's got a fixed positive negative charge. There's no long way for them to interact with each other. So they are not going to be soluble in each other. And we get these distinct phases that occurs. And this brings up a really important sort of idea when we talk about sort of the solubility of things in each other. And that's the idea you hear a lot of, but people say like dissolves like. And what that really means is things that have similar intermolecular forces or similar ways of interacting with each other will be soluble in each other. Things that really do not use similar types of intermolecular forces will not be soluble in each other. And that's really where we get kind of our three groups of things that are sort of soluble and our guys that really are insoluble. That means that things that are typically soluble in each other is if you take a polar guy and a polar guy, that's all good. If you actually take a non-polar guy and a non-polar guy, that's okay as well, because they're both going to be using dispersion forces, which is the same type of forces. If you take an ion and a polar guy, that's going to be okay because they're going to use that ion dipole interaction, which is a very similar sort of interaction. You really only run into some problems there with insolubility when you kind of cross over a polar guy like water with something that's non-polar like carbon tetrachloride. This also brings up a point that I mentioned a while back there when we were talking sort of about solvents, for example. So sometimes people think, you know, the solvent all the time it should be water, right? Water is a good solvent, and it is a good solvent for a lot of things. It's a very good solvent for things that are polar. It's a good solvent for things that are ionic, because again, if you use water with something polar, they both could use dipole-dipole interaction or hydrogen bonding. If you use water with something that's ionic, it'd do an ion-dipole interaction. But if you try to use something like water with, again, something like carbon tetrachloride is not a good solvent because of that. It doesn't work well with nonpolar things. So if you do have something that's nonpolar, you need like a nonpolar solvent if you want it to get it to dissolve and stuff like that. So sometimes you do see something like carbon tetrachloride. Also, like we saw it when we did that experiment way back when we started at the beginning, where we used the hexane and our halogens, which like our Br2, our Cl2, our I2. Those guys are non-polar, required not water, because it wouldn't stay in the water layer, if you remember. It went up to the hexane, which is a non-polar solvent, up into that layer. So again, like dissolves like, gets things to basically mix, and it's something you hear a lot when we talk about solubility. And again, so you don't see these different sort of layering that happens when we do have obviously something that is immiscible in each other and not really soluble in each other. Now let's talk a little bit about solubility in water. We talked about solubility rules, but in general, typically if we're talking about water and things really sort of being able to dissolve, and that's really what we're talking about, you know, mixing well, dissolving well. If we're talking about something that's soluble in water, ionic compounds are definitely soluble in water. Again, they have that ability to basically to do that ion dipole interaction in terms of that intermolecular forces. And as we talked about a number of times throughout the semester, you know, when we take something that's an ion and put it into water, those ions basically do get surrounded by water, right? And because water is polar, doing that ion dipole interaction, it's what allows something like, say, salt that you put into water to dissolve and look like it sort of disappeared, but in reality it really didn't. It just got caught up in all the water matrix there, and to our visual eye it looks like it went away and it's gone and it disappeared, but it's able to do again that sort of ion dipole interaction that we talked about in terms of intermolecular forces. But as we just saw there in that example, ethanol, which is non-ionic, sort of covalent molecules, and even sugar can be soluble in water. And that brings up a good point. Why are those guys soluble in water? Well, as we just saw there in that picture, ethanol, even though it's not ionic and it's got sort of that non-polar part, as we saw in the picture, it contains this really important polar part. And that polar part, again, is pretty much identical to what you see in water, and it gives it a place to interact well with water. Also, ethanol is not very large, so it's able to do that interaction. The solubility of things, for example, like ethanol, that does have that OH, but has carbons and hydrogens and sort of this nonpolar part. The solubility decreases a lot after about 6 carbons or so. So if you built out this thing with 6 or more carbons and just this one lonely OH bond there at the end, the solubility decreases a lot to almost being insoluble in water at that point, because 2 things happen. Basically, in order for something to be soluble in water, you got to punch holes in water and replace water and water interactions with similar types of interactions. And when you start to get something that's really, really big, it doesn't fit really well with all the water and water molecules. Sucrose, which is a relatively larger molecule, is able to be soluble in water, which is sugar. And even though it's a little bit larger of a molecule, it's able to compensate for that because it is pretty much, as we'll see in the picture, littered with OH bonds all over it. So it's got OH bonds all over it. Everywhere there's an OH bond, it gives something like sugar an opportunity to interact well with water. And again, through our hydrogen bonding, that's actually methanol there, which again, this part here where our carbon is nonpolar, but containing this OH bond and allowing it to do some hydrogen bonding with the water molecules, which means it would be soluble in it. That's our ethanol that we talked about. So what about oil and water? They really don't mix. So as we talked about, oil is pretty much nothing more than just a very long chain of carbons and hydrogens together. And because carbon and hydrogen is pretty much non-polar, because when we do the carbon-hydrogen bond, the difference is 0.4 when we do that. Oil is insoluble in water is probably a better way to word that there. It's insoluble in water. And it's really for the same reason. Oil, which is pretty much non-polar, is going to be trying to use dispersion forces, while again, water, which is polar, is going to be using hydrogen bonding. So again, we get this conflict in the type of intermolecular forces that these guys are going to try to use. And as I was just speaking about, basically anytime we want to kind of insert anything into water, we basically have to break these bonds between water and water, and again, replace them with similar bonds and kind of similar size molecules. So when we get something like oil, which is a very long chain of carbons and hydrogens, you know, it's kind of like you have your car in your garage, for example, you know, and it fits, right? So we go, okay, well, I could definitely open the garage. I could definitely pull out, perhaps your car, and, you take like a big semi truck or something like that, or something big giant limousine or something so it'll actually fit height wise. Take a limousine, big giant limousine, you try to pull it into your garage. Yeah, it kind of fits, but it really doesn't fit right. It's kind of hanging out and stuff like that. So it really doesn't fit well into that space. And it's a similar thing that happens with something like oil. Although, it can do a short-term interaction doing some dispersion forces because of the sheer size of it. It just doesn't really interact really well. You can't shut your garage door. This doesn't really mix really well. So what we end up doing is getting the separation that occurs, and the oil sort of floats to the top, and obviously the water is on the bottom there. And again, that comes back to the idea of, as we talked about, sort of like dissolves like, where things with similar intermolecular forces will interact well with each other, and things with non-similar intermolecular forces will not be pretty much soluble or interact well with one another. Any questions on that there? Okay, probably a good stopping spot there. So we'll stop here.